taller, higher, faster. With no bounds to human ambition and technological advancements to match, megaprojects around the world are becoming crazier and crazier. But which of humanity's greatest creations sit at the pinnacle? From the world's tallest towers to the race for its next tallest building, and from biggest airports ever built to train journeys matching the speeds of commercial flights, these are the megaprojects creating the most insane world records. Stay with us as we go from continent to continent to bring you the most fascinating stories of the world's most unbelievable megabuilds. Starting with the Tokyo Tower was completed in 1958, and it was an engineering marvel for its time. Standing at 333 meters tall, this steel giant was modeled loosely on the Eiffel Tower. It dominated the Tokyo skyline and had to be painted in bright orange and white so aircraft wouldn't fly into it. Its main purpose was to broadcast television and radio signals across one of the world's most populated cities. But Tokyo didn't stay still. Through the 60s, 70s, and 80s, the city kept building upward. Skyscrapers multiplied across the skyline, and each new tower that went up created a new obstacle for the Tokyo Tower's signals. By the time the 2000s arrived, the broadcast quality across the city had deteriorated badly. Signals were bouncing off buildings, creating interference that no software patch could fix. The tower that had served Tokyo for half a century was being strangled by the very city it was built to serve. Engineers and city planners had known this day was coming. The only real solution was a new tower, one tall enough to broadcast from above the entire skyline, no matter how high Tokyo's buildings climbed. And if they were going to build it, they were going to build it properly. Planning for the Tokyo Skytree began in the early 2000s with close to 100 architects and engineers involved in the design process. The brief was straightforward. They were going to build the tallest tower in the world. Its design, inspired by traditional Japanese architecture, has a lower triangular cross-section that gradually transitions into a circle as it rises, mimicking the shape of a Japanese pagoda. While the curves of the exterior were deliberately styled after the blade of a samurai sword, but beauty was secondary to survival. Japan sits on the Pacific Ring of Fire and experiences 10% of all seismic activity on the planet, more than almost any other nation on Earth. Building a structure this tall in Tokyo meant building something that could absorb the kind of punishment that flattens ordinary buildings. To fight the elements, the outer structure and the central pillar of the Tokyo Skytree move independently, absorbing seismic energy rather than fighting it. The result is a tower engineered to withstand a magnitude 8.0 earthquake. Construction of the Skytree began in 2008 and took 4 years. When completed in 2012, it stood at 634 meters tall, a number chosen deliberately since 6, 3, and 4 can be read in Japanese as mu, sa, and shi, an old name for the Musashi region where Tokyo sits. It overtook China's Canton Tower to claim the title of the world's tallest tower, and it did so by a significant margin. At a cost of around $800 million, it became the new broadcasting backbone of the city, its signals now sailing cleanly over every rooftop in Tokyo. The Skytree also became an instant tourist destination. 2 observation decks sit at 350 and 450 meters above the ground, offering views across the entire Kanto Plain on clear days, all the way to Mount Fuji. Since opening, the tower has welcomed over 50 million visitors. Before we go further, there's a distinction worth making. The Tokyo Skytree is the tallest tower in the world, but it is not the tallest building. That title belongs to the Burj Khalifa in Dubai, which stands at 828 meters. The difference comes down to what constitutes a building. The Burj Khalifa has floors, offices, apartments, and hotels. People live and work inside it. The Tokyo Skytree, by contrast, is a tower. Most of its height is structural, built around equipment and engineering rather than habitable space. The same distinction separates the CN Tower in Toronto from the skyscrapers around it, or the Ostankino Tower in Moscow from the surrounding city. Towers and buildings compete in different categories, which is why both the Skytree and the Burj Khalifa can each claim a world record without contradicting each other. What's interesting is that the Skytree's record may not last forever. Dubai, in addition to holding the record for the tallest building, has floated plans for a tower that would push past 1,000 meters. Saudi Arabia has been developing its own record-chasing ambitions. And in Tokyo itself, there have been quiet discussions about what the next generation of broadcasting infrastructure might look like as streaming continues to erode traditional broadcast media. Whether the Skytree will still be wearing its crown in 20 years is genuinely uncertain. For now, though, it stands unchallenged, a structure that solved a very practical problem and ended up becoming one of the most visited landmarks on Earth in the process. And if towers are impressive, wait until you see what happens when architects are allowed to fill every single meter with floors, glass, and steel. Because over in the Middle East, the race to build the tallest building in the world is getting hotter. For most of the 20th century, the race to build the world's tallest building was essentially an American sport. New York and Chicago traded the crown back and forth for decades. From the Chrysler Building to the Empire State Building to the Twin Towers to the Sears Tower in Chicago, which held the record for a full 25 years. Then in 1998, something shifted. The Petronas Towers opened in Kuala Lumpur, Malaysia, and for the first time in a century, the tallest building on Earth was not in the United States. At 452 meters, the twin skyscrapers announced to the world that the race had gone global. It didn't stay in Malaysia for long. By 2004, Taiwan's Taipei 101 had climbed to 508 meters, the first building ever to crack the 500-meter mark, and it claimed the crown. But what happened next was something that nobody in the skyscraper world had quite seen before. Dubai looked at Taipei 101, looked at the record, and decided it wasn't going to inch past it. It was going to obliterate it. The Burj Khalifa opened in January 2010 at 828 meters tall, more than 300 meters higher than the building it replaced as world number 1. To put that gap in perspective, the margin by which the Burj Khalifa beat Taipei 101 is larger than the entire height of the Chrysler Building. It didn't just take the record, it made every previous record seem almost quaint by comparison. The project cost around $1.5 billion and took roughly 6 years to build, with over 12,000 workers on site at the peak of construction. It has 163 floors, holds a hotel, offices, and residential apartments, and its observation deck on the 124th floor draws well over 1 million visitors every year. More than 15 years after opening, the Burj Khalifa is still the tallest building in the world, and no structure has come close to threatening that title until now. Two challengers are taking shape, and in a twist that feels almost poetic, both are coming from the same corner of the world that dethroned America back in 1998. The first is already rising on Dubai's own Sheikh Zayed Road, just a couple of kilometers from the Burj Khalifa itself. The Burj Azizi, developed by Azizi Developments, is planned to reach 725 meters across 133 floors, which would make it the second tallest building on Earth the moment it opens. Construction began in early 2024, and the tower is targeting completion around 2028 or 2029. It will house a 7-star hotel, luxury residences, and a stack of world records of its own, including the highest observation deck, the highest hotel lobby, and the highest restaurant ever built. So Dubai, already home to the tallest building in the world, is quietly building the second tallest one too. But the more dramatic story is happening in Saudi Arabia, and it has been a long time coming. The Jeddah Tower, which spent years being called the Kingdom Tower before a rename, was supposed to be a straightforward exercise in ambition. Construction began in 2013, and the plan was simple enough on paper: build the world's first kilometer-tall skyscraper at over 1,000 meters and plant it on the Red Sea coast in Jeddah. The original completion target was 2020. Then almost everything that could go wrong did. In late 2017, Saudi Arabia's Crown Prince Mohammed bin Salman launched a sweeping anti-corruption crackdown that rounded up hundreds of businessmen and officials at the Ritz-Carlton in Riyadh. Among those detained was the chairman of the Saudi Bin Laden Group, the project's main contractor, and a key figure in the conglomerate co-financing the tower. construction quietly limped along for a few more months before grinding to a complete halt in early 2018. For nearly 7 years, one of the most ambitious construction projects ever attempted sat frozen, roughly a third complete, cranes idle above the Jeddah skyline. When construction finally resumed in January 2025, the contractor brought back to finish the job was the same Saudi bin Laden group whose chairman had been arrested in the first place, rehired under a new contract worth close to $2 billion. The pace since restart has been striking. Workers have been adding roughly a new floor every 3 to 4 days, using high-pressure concrete pumps pushing material to heights that have never been attempted before. By January 2026, the structure had reached its 81st floor, with engineers estimating the tower will pass the 100th floor by April. Out of 157 total floors, more than half the concrete work is now complete. The architect behind the Jeddah Tower is Adrian Smith, who also designed the Burj Khalifa, which makes this an unusual situation where the same person is effectively designing both the current world record holder and its replacement. The structure uses a 3-petal footprint, each wing tapering as it rises, not just for aesthetics, but to shed wind vortices that at a kilometer of altitude would otherwise shake the building in ways that no conventional design could manage. When it opens, currently targeted for August 2028, it will stand roughly 180 meters taller than the Burj Khalifa and house the highest observation deck ever built, overlooking the Red Sea. And yet, even the Jeddah Tower may eventually be surpassed. Saudi Arabia's own planning documents include a proposal for a structure in Riyadh called the Rise Tower, with a reported target height of 2 full kilometers. That project is still in early planning stages and nobody should hold their breath. Similar proposals have been floated for Dubai Creek Tower and for Burj Mubarak Al Kabir in Kuwait. However, none of those plans are concrete. For now, it's Saudi Arabia's turn to take the world record and to keep it for years to come. From high up in the sky, we go deep into the ground as we take a closer look at some record-breaking tunnels from around the world. On a June day in 2016, when a freight train slipped beneath the Swiss Alps through the Gotthard Base Tunnel and emerged on the other side 57 kilometers later. It was the longest railway tunnel ever built, and it had taken 17 years and around $12 billion to create. The problem the Gotthard Base Tunnel was built to solve had been building for decades. Switzerland sits at the heart of Europe's north-south trade corridor, and by the 1990s, the volume of freight crossing the Alps had become a genuine crisis. Most of it moved by truck through mountain roads that were congested, dangerous, and almost impossible in winter. The environmental damage from heavy vehicles grinding through some of Europe's most sensitive landscapes had become a political issue. In 1992, Swiss voters approved the project in a referendum, and in a follow-up vote a few years later, they also backed a plan to shift all goods crossing Switzerland from road to rail. The tunnel was the centerpiece of that ambition. What made building it so extraordinary was the geology. The Alps are not a uniform mass of rock. As the boring machines worked their way through 57 kilometers of mountain, they encountered granite, gneiss, fractured zones where water poured in under pressure, and sections where the rock temperature climbed above 40 degrees Celsius. Workers drilled and blasted through 28 million tons of rock over the course of construction, most of which was recycled into the concrete used to line the tunnel itself. At its deepest point, the tunnel sits 2,300 meters beneath the mountain peaks above it, which means the pressure bearing down on the structure is roughly equivalent to a column of rock taller than the Eiffel Tower stacked 7 times over. The result transformed freight movement across Europe. Over 200 freight trains now use the tunnel every day, each one carrying goods that would otherwise be on trucks. Passenger trains pass through at speeds of up to 250 kilometers per hour, cutting the journey between Zurich and Milan to around 3.5 hours. The full crossing takes less than 20 minutes. While the Gotthard holds the record for the longest railway tunnel in the world, a separate and older record belongs to Japan. The Seikan Tunnel, completed in 1988, stretches 53.85 kilometers beneath the Tsugaru Strait connecting the islands of Honshu and Hokkaido, making it the longest undersea tunnel by total length. But while the SIGNUM is longer than the Channel Tunnel between England and France, its actual underwater section is only 23 kilometers. The Channel Tunnel's underwater portion runs for 38 kilometers, making it the longest continuous undersea section of any tunnel in the world, even though its total length of 50 kilometers falls short of SIGNUM overall. Both of those tunnels were built by boring machines cutting through rock beneath the seabed. The next record holder will be built by a completely different method, and it is currently taking shape on the floor of the Baltic Sea between Denmark and Germany. The Fehmarn Belt Tunnel, when complete, will be the world's longest immersed tunnel. The distinction matters because immersed tunnels are not bored through rock. They are prefabricated on land in enormous concrete sections, floated out to sea, sunk into a trench, dredged into the seabed, and locked together underwater. The Fehmarn Tunnel will consist of 89 such elements, each one 217 meters long and weighing around 73,000 tons. Together, they will form an 18-kilometer crossing beneath the Baltic Sea, connecting the Danish island of Lolland with the German island of Fehmarn, carrying both a 4-lane motorway and twin electrified rail tracks in a single structure. The cost is around 7.4 billion euros. The scale of what is happening on the seabed is difficult to visualize from above. A dredging operation that took 3 years removed 15 million cubic meters of soil and sand from the Baltic floor to create the trench the tunnel will occupy. That excavated material is being used to build 300 hectares of new coastal land near the Danish construction site. The tunnel factory on the island of Lolland, purpose-built for this project, is one of the largest concrete production facilities in Europe, casting segments around the clock with welding robots assembling the steel reinforcement skeletons before each pour. By early 2026, several completed elements were already floating in the basins outside the factory, waiting for immersion to begin in earnest. When it opens, around 2031, given the approval delays on the German side, crossing the Fehmarn Belt will take 10 minutes by road and 7 by train. The ferry that currently serves the route takes 45 minutes. The journey from Copenhagen to Hamburg, which currently takes around 4.5 hours by rail, will drop to 2.5 hours. Over in Norway, a different kind of tunnel record is taking shape beneath the fjords. The Rogfast Tunnel, expected to open in 2033, will not be the longest tunnel in the world, but it will be the deepest. Stretching 26.7 kilometers through solid bedrock beneath the Boknafjord in western Norway, it will reach a maximum depth of 392 meters below sea level. That is deeper than the SIGNUM, deeper than the Channel Tunnel, deeper than anything like it that has ever been built. Unlike the Fehmarn Tunnel, which sits in a trench on the seafloor, Rogfast is being drilled and blasted through the rock itself, in a method Norway has refined over decades through its network of around 40 existing subsea road tunnels. The engineering challenge that makes Rogfast particularly striking is the precision required. Teams are boring from both ends simultaneously and must meet in the middle with a margin of error of just 5 centimeters across 26 kilometers of rock. Sensors embedded in the tunnel walls feed data to a digital model of the structure in real time, flagging any deviation before it becomes a problem. Saltwater infiltration through fractured rock at that depth is a constant issue, requiring continuous grouting and sealing as the excavation progresses. Roughly halfway through the tunnel, at 260 meters below sea level, a double roundabout will be built to connect a spur leading to Kvitsøy, Norway's smallest municipality, an island that currently has no fixed link to the mainland. It will be the deepest road junction ever constructed. When it all opens, Rogfast will cut travel time between Stavanger and Bergen by 40 minutes and eliminate several ferry crossings that currently make the journey along Norway's west coast, as much a maritime operation as a road trip. Each of these tunnels is a different answer to the same problem: geography, the Alps, the Tsugaru Strait, the Baltic Sea, the Norwegian fjords. What changes with every generation of engineering is simply how much further underground the answer can be found. Tunnels underwater are impressive feats of engineering, and so are megabridges built high up in the sky. And one country in particular is winning that race. For over 2 decades, the Millau Viaduct in southern France held the title of the world's tallest bridge. Completed in 2004, it stretches 2.4 kilometers across the valley of the Tarn River, and its tallest mast rises 343 meters from the valley floor, taller than the Eiffel Tower. Designed by Norman Foster and French engineer Michel Virlejeu, it solved a problem that had plagued the A75 motorway for decades. Every summer, hundreds of thousands of drivers heading from Paris to the Mediterranean would grind to a standstill trying to navigate the valley near the town of Millau, sometimes sitting in traffic for hours in the summer heat. The viaduct completed the missing link and cut the crossing to minutes. Building it was an engineering feat in its own right. 7 concrete piers had to be positioned with satellite precision across the valley floor. The tallest of them, nearly 245 meters high, taller than any bridge pier ever built before. The road deck was assembled on flat land on both sides of the valley, and then pushed out incrementally over the tops of the piers using synchronized hydraulic jacks, centimeter by centimeter, until the two halves met above the Tarn within 1 centimeter of perfect alignment. For a structure 270 meters above the river at its peak, that margin of error is almost absurd. The bridge cost around 400 million euros and has carried nearly 5 million vehicles a year since opening. It held the structural height record for 21 years. Then, in late 2025, a new bridge in China's Guizhou province quietly took it. Before we talk about the new record holder, let's make a key distinction between the tallest and highest bridges in the world. When engineers talk about the tallest bridge in the world, they mean structural height, measured from the top of the bridge's towers or masts down to where the structure meets the ground. When they talk about the highest bridge, they mean deck height, the distance from the road surface itself down to whatever is below it, whether that's a river, a gorge, or open air. These are completely different measurements, and for more than a decade, Millau Viaduct held both records. Then China arrived, and the record stopped belonging to the same structure. Before losing the record for tallest bridge, Guizhou had already stolen the highest bridge title. In 2016, the Doog Bridge opened over the Beipan River Gorge, with its road deck sitting 565 meters above the water, nearly twice the deck height of the Millau Viaduct. It seemed an almost untouchable number. But then, in September 2025, the Huajiang Grand Canyon Bridge opened just over 100 kilometers away, also over the Beipan River, with its deck 625 meters above the gorge below. The entire Empire State Building could fit beneath it with 180 meters to spare. It is 9 times higher than San Francisco's Golden Gate Bridge and more than twice the height of the highest bridge in the United States. A journey that used to take 2 hours of switchback mountain driving now takes 2 minutes. The bridge also holds the world record for the longest span of any steel truss suspension bridge in mountainous terrain, with its main span stretching 1,420 meters between 2 towers. Both of these record-breaking bridges are in Guizhou province, and that is not a coincidence. Guizhou is among the most mountainous and historically impoverished regions in China. In the 1980s, the entire province had fewer than 3,000 bridges. Today, it has over 32,000, and the province is now sometimes called the world's bridge museum. China's decision to pour extraordinary engineering resources into Guizhou was deliberate. The terrain made roads almost impossible, which kept the region poor and isolated, so bridges became the instrument of economic development. Chinese engineers have spent 3 decades perfecting the art of building in extreme mountain conditions, which is why the world's 7 highest bridges are all in China, and nearly half of the world's 100 highest bridges are in Guizhou alone. From the mid-1990s onward, China made the decision to build out a national highway and high-speed rail network at a speed and scale that no country had ever attempted. Many records have fallen since, including the longest bridge ever built, and it is not close. The Danyang-Kunshan Grand Bridge in eastern China stretches 164.8 kilometers along the Beijing-Shanghai high-speed railway, connecting Shanghai with Nanjing across a landscape of rivers, rice paddies, lakes, and canal networks that would have been a nightmare to build a conventional railway through. It opened in 2011 and has held the world record ever since. The construction employed 10,000 workers over 4 years and cost $8.5 billion, which works out to roughly $51 million per kilometer. Before the bridge, a train journey between certain cities along the route took 4.5 hours. After it, the same trip takes 2. Unlike the towering structures of Guizhou, the Danyang-Kunshan Bridge sits only about 30 meters above the ground on average. Its scale is the record, not its height. And like almost everything else in the world of bridge building right now, it is a record held by China. Building taller, higher, and longer bridges has been made possible with unparalleled advancements in engineering, a running theme through all the mega projects in this video, particularly when it comes to building the world's biggest record-breaking aviation hubs. King Fahd International Airport near Dammam covers 780 square kilometers. That is not a typo. The entire country of Bahrain fits inside it with room to spare. New York City's 5 boroughs combined would fit inside it. Paris, the city itself, would occupy less than an eighth of the total footprint. The airport holds the Guinness World Record for the largest airport on Earth by land area, a title it has held since it opened in 1999. Why they built so big is simple. Saudi Arabia has too much desert. They had a blank stretch of land and no limits. However, there's a caveat. Only a fraction of that land is actually in use. The active terminal and runway areas cover roughly 37 square kilometers. The rest is undeveloped desert, much of it reserved for future expansion, along with a military airfield operated by the Royal Saudi Air Force, a plant nursery, a mosque with capacity for 2,000 worshippers, and residential housing for 3,000 airport employees. In Saudi Arabia, apparently, even the airport's infrastructure needs a suburb. The airport sees around 10 million passengers a year, modest by global standards, and operates primarily as a regional hub connecting the eastern province to destinations across the Middle East and Indian subcontinent. Size alone, then, is not the same as significance, which is where Atlanta comes in. Hartsfield-Jackson Atlanta International Airport covers just 19 square kilometers, less than a single district of King Fahd's total property. But in 2024, 108 million passengers moved through it, making it the busiest airport on the planet for the 26th consecutive year. That works out to roughly 296,000 people every single day passing through a facility smaller than many university campuses. The reason Atlanta dominates is geography and strategy in equal measure. The city sits at the demographic center of the American Southeast, roughly equidistant from nearly every major U.S. population center, which made it a natural connecting point long before airlines existed. When Delta Airlines turned Atlanta into its primary hub in the late 1970s and adopted the hub-and-spoke system early, it transformed the airport into a funnel for the entire country. Today, Delta operates nearly 3/4 of all flights at Hartsfield-Jackson, running over 1,000 daily departures to more than 225 destinations. The result is an airport where the vast majority of passengers are not actually going to or from Atlanta. They are simply passing through it on the way somewhere else. In 2015, Hartsfield-Jackson became the first airport in history to handle more than 100 million passengers in a single year. No other airport has matched it since. That record may not stand forever, though, because Dubai is planning something extraordinary. Dubai International Airport already ranks second in the world by passenger volume, handling over 92 million travelers in 2024 on the back of Emirates' enormous global route network. But the airport is landlocked, surrounded on all sides by urban development, and physically unable to grow further. Dubai's answer to that problem is not to expand the existing airport. It is to build an entirely new one from scratch and eventually shut the old one down. Al Maktoum International Airport, already partially operational as a cargo and secondary passenger hub southwest of the city, is set to become the largest airport ever built. In April 2024, Dubai's ruler approved a $35 billion expansion program that will eventually give the airport 5 parallel runways, over 400 aircraft gates, and a passenger capacity of 260 million per year. This is more than double the current volume of the busiest airport on Earth. At 70 square kilometers once complete, the facility will be roughly 5 times the physical size of the existing Dubai International Airport, with an entire new city of 1 million residents being built around it as part of the broader Dubai South development. Emirates and Fly Dubai are expected to shift all operations there by 2032, at which point Dubai International would effectively close. A city dismantling one of the world's top 5 busiest airports to replace it with something more than twice as large is about as clear a statement of ambition as any country has made in modern aviation. But before Dubai could even dream of building airports at this scale, Japan had already pulled off something that the rest of the engineering world thought was bordering on impossible. By the 1980s, Osaka was running out of options. The city's existing airport sat in the middle of a densely populated urban area. Noise complaints had restricted it to daytime flights only, and there was no land nearby for expansion. The solution the Japanese government arrived at was audacious: build a new airport in the middle of Osaka Bay, 5 kilometers offshore, on an artificial island that did not yet exist. Construction of Kansai International Airport began in 1987. Workers dredged millions of tons of sand and rock from 3 separate mountains and dumped them into 20 meters of open water, building up an island from scratch. Over 2 million sand drainage pipes were driven into the seabed clay to force the water out of the sediment and stabilize the ground. A 3.75-kilometer bridge was built to connect the island to the mainland. The terminal, designed by architect Renzo Piano, stretched 1.7 kilometers in length, shaped like an aircraft wing from above, and was mounted on 900 hydraulic columns that could each be individually adjusted as the ground beneath them shifted. The entire project cost around $20 billion and took the better part of a decade. Kansai opened in September 1994 as the world's first airport built entirely on an artificial island. Engineers had predicted the island would sink roughly 6 meters as the weight of the construction compressed the soft clay seabed beneath it. By 1999, it had sunk more than 8 meters, nearly 50% beyond the worst-case estimate. The seawall had to be raised at an additional cost of over $150 million. Typhoon Jebi hit the airport in 2018, flooding the runway and stranding thousands of passengers after a tanker ship collided with the only bridge to the mainland. The island is still sinking today, though the rate has slowed dramatically from 50 centimeters per year in 1994 to around 6 centimeters annually now. Some engineers project that, without continued intervention, sections of the island could reach sea level by the mid-21st century. Despite all of that, the American Society of Civil Engineers ranked Kansai International among the 10 civil engineering achievements with the greatest impact on human life in the entire 20th century, alongside the Panama Canal and the Channel Tunnel. The project proved that you could build a full international airport on reclaimed ocean water, and once it proved that, others took note. China has taken note more than anyone. The country is currently constructing an airport on an artificial island off the coast of Dalian, a port city of 8 million people in northeastern China that has long been a major trade hub for commerce with Japan and South Korea. Dalian's existing airport, built during Japanese occupation nearly a century ago, has been expanded 5 times and is now completely surrounded by urban development with nowhere left to grow. The solution mirrors Kansai, but on a scale that makes Kansai look modest. Dalian Jinzhouwan International Airport is being built on 21 square kilometers of reclaimed land in Jinzhou Bay. When complete, it will be the largest artificial island airport ever constructed, nearly double the size of Hong Kong International Airport, which currently holds that title. The project costs an estimated $4.3 billion and poses geological challenges that even China's construction industry finds significant. The rock-embedded foundation piles each run up to 80 meters deep, 3 times the depth required for a conventional land airport, driven through complex and unpredictable seabed conditions. 4 runways and a terminal handling up to 80 million passengers annually are planned for full build-out, with the first phase targeting completion by 2035. What Kansai proved with $20 billion and a decade of effort in the 1990s, China is now replicating at twice the scale. The idea of an airport rising out of the sea, once a near impossibility, has become simply another item in the infrastructure playbook. Airports built on sea are becoming more common, but when it comes to sprawling infrastructure, some of the greatest megaprojects in history are the ones aimed at harnessing rivers. The Yangtze River has flooded catastrophically for as long as Chinese civilization has existed along its banks. Entire provinces would go underwater. In 1931, a series of floods along the Yangtze killed somewhere between 1 and 4 million people, one of the deadliest natural disasters in recorded history. For a country with the world's largest population, sitting on relatively modest fossil fuel reserves but crisscrossed by some of the most powerful river systems on Earth, harnessing that water was never just an engineering ambition. It was a national survival strategy. No project embodied that more completely than the Three Gorges Dam. The idea of damming the Yangtze at the Three Gorges had been discussed since 1918, when Sun Yat-sen first proposed it. Serious planning began in the 1950s. Construction finally started in 1994, and what followed was 17 years of work on a scale that had no precedent in dam building history. The dam wall stretches 2,335 meters across the river, nearly 1.5 miles of solid concrete, standing 185 meters tall at its highest point. Workers poured 28 million cubic meters of concrete into it. To put that in context, the Hoover Dam used around 3.3 million cubic meters. The Three Gorges Dam used nearly 9 times as much. The reservoir it created stretches 600 kilometers upstream, flooding an area larger than the state of Rhode Island and requiring the permanent relocation of over 1.3 million people from towns, villages, and farmland that now sit beneath the water. The dam became fully operational in 2012, when the last of its 32 main turbines came online. At that point, it became the largest power station on Earth by installed capacity, a title it still holds, generating up to 22,500 megawatts. For comparison, the United States' largest hydropower facility, the Grand Coulee Dam in Washington state, generates 6,800 megawatts. Three Gorges produces more than 3 times as much and more than 10 times the capacity of Nevada's Hoover Dam. In a single year, its 32 generators, each spinning at 700 megawatts, produce enough electricity to run entire nations. In 2020, following an unusually heavy monsoon season, the dam generated 111.8 terawatt-hours of electricity in a single year, breaking the world record for annual output from a single hydropower station, a record previously held by the Itaipu Dam on the Brazil-Paraguay border. The electricity generated that year was equivalent to burning 34 million tons of coal without the coal. Three Gorges also fundamentally changed what the Yangtze means as a shipping route. The reservoir's depth now allows 10,000-ton ocean-going freighters to navigate 2,250 kilometers inland from Shanghai all the way to the city of Chongqing, a reach that was previously impossible. A 5-stage shiplock system lets vessels climb or descend 113 meters to pass the dam, the equivalent of scaling a 40-story building, and a separate ship lift handles smaller vessels even faster. The dam paid back its entire construction cost of roughly $23 billion by December 2013, just over a decade after it began producing power. China did not stop there. Running along the same river system as Three Gorges, the country has since built a cascade of additional megaprojects, creating what it calls a clean energy corridor. The Baihetan Dam, completed in 2022 on the Jinsha River upstream, is the second largest hydropower station in the world at 16,000 megawatts of installed capacity. It introduced something new, even by Chinese standards. Each of its 16 turbines generates exactly 1,000 megawatts individually, making them the most powerful single hydroelectric turbines ever built. Baihetan stands 289 meters tall, nearly as tall as the Eiffel Tower, and its turbines eliminate the need to burn approximately 20 million tons of coal every year. The reason China builds at this scale comes down to geography and necessity. The country is the world's largest energy consumer, with a population of 1.4 billion and an industrial economy that runs around the clock. Its domestic coal reserves are significant but finite. Its oil imports leave it exposed to geopolitical disruption, and its southwestern provinces sit on some of the most powerful undeveloped river systems anywhere on Earth, fed by Himalayan snowmelt and monsoon rainfall in volumes few other countries can match. Hydropower offers China something it cannot easily get elsewhere: energy independence from a domestic source that refills itself every year. Even against that backdrop, what China approved in December 2024 is something different in kind. The Medog hydropower station on the Yarlung-Changpo River in Tibet began construction in July 2025. The Yarlung-Changpo is the highest major river in the world by altitude, and at its Great Bend in Medog County, it does something extraordinary. In just 50 kilometers, the river drops over 2,000 meters in elevation, plunging through the world's deepest canyon on its way to becoming the Brahmaputra in India. That vertical drop, concentrated over such a short distance, contains more hydropower potential per kilometer than almost any other river on Earth. China is going to harness it. The project will consist of 5 cascade hydropower stations built along that canyon, with 4 tunnels each around 20 kilometers long bored straight through the Namcha Barwa mountain to divert the river through the turbines. Total installed capacity will be 60,000 megawatts, nearly 3 times the capacity of 3 gorges. Projected annual output is 300 billion kilowatt hours, enough to power the entire United Kingdom for a year, or supply electricity to 300 million people. The total investment is approximately 1.2 trillion yuan, around $167 billion, making it one of the most expensive infrastructure projects in human history. Commercial operations are targeted for 2033. The project has drawn significant concern from India and Bangladesh, both downstream nations whose populations depend on the Brahmaputra and its tributaries for water, agriculture, and flood management. China maintains the project will not meaningfully reduce downstream flows, since the majority of the Brahmaputra's annual discharge originates from monsoon rainfall within India itself, rather than from the Tibetan upper reaches. The engineering challenges are equally formidable, with the Great Bend sitting in one of the most seismically active zones on the planet, where the Indian and Eurasian tectonic plates are still colliding. Whether China can deliver on its 2033 target in terrain, this complex remains to be seen. But the ambition of the project is not in doubt. 3 Gorges was once described as China's project of the century. Medog, on every metric, is bigger. So far, we've talked about tall skyscrapers, massive dams, longest tunnels, and highest bridges. But we end today's video with a different world record: the fastest bullet trains, all of them concentrated in Asia. China has built the largest high-speed rail network in human history. By the end of 2025, it surpassed 50,000 kilometers of high-speed track, more than 2/3 of everything that exists in the entire world. That network connects 96% of all Chinese cities with populations over 500,000 people. But even by China's own extraordinary standards, one line stands in a category of its own. It is the Shanghai Maglev, the fastest train on Earth. To understand what makes it special, you first need to understand what a maglev train actually is. A conventional high-speed train, no matter how fast, still runs on wheels that make physical contact with a rail. At extreme speeds, that contact creates friction, vibration, and wear. The faster you go, the harder that problem becomes to manage, reducing speed. Maglev solves it by removing contact entirely. The train floats. Powerful electromagnets embedded along the guideway generate opposing magnetic fields that lift the vehicle several centimeters off the track and propel it forward simultaneously, with no wheels, no axles, and no physical connection between the train and the surface beneath it. The only resistance left to overcome is air, which is why maglev trains can reach speeds that conventional wheels can never match. In the late 1990s, Shanghai needed a fast link between Pudong International Airport and the city's eastern financial district, 30 kilometers away. Traffic by road took 45 minutes. The city looked at its options and decided to do something no one had done before: build the world's first commercial high-speed maglev line. The technology came from Germany, developed by a joint venture between Siemens and ThyssenKrupp under the Transrapid program, which had spent decades refining maglev engineering on test tracks without ever convincing any government to build a revenue-generating line. Shanghai became the proving ground. Construction began in March 2001. Workers built an elevated guideway stretching 30 kilometers across the outer districts of Pudong, fabricating the stator packages that power the train in Kassel, Germany, and shipping them to Shanghai for installation at 25-meter intervals along the entire route. The total cost came to roughly $1.2 billion. Less than 3 years later, in April 2004, the line opened to fare-paying passengers. The numbers it posted were like nothing land transport had produced before. At peak operation, the Shanghai Maglev ran at 431 kilometers per hour, covering the airport-to-city distance in 8 minutes. To feel what that means, a journey that would take 45 minutes by road took 8. The train reaches 350 kilometers per hour within 2 minutes of leaving the station. During a test run in November 2003 before commercial service began, a 5-car train set recorded 501 kilometers per hour, becoming the fastest ground vehicle on Earth at that moment. For 17 consecutive years, from its opening in 2004 until 2021, the Shanghai Maglev held the title of the fastest train in regular commercial operation anywhere in the world. The line has not been without complications. Early ridership was low because the terminal at Longyang Road sits on the outskirts of Pudong rather than in the city center, forcing passengers onto a further metro transfer to reach their destinations. Ticket prices ran several times higher than the metro. In its first years, the operating company ran significant losses, and proposals to extend the line deeper into Shanghai repeatedly stalled over concerns from residents about electromagnetic fields and falling property values. By 2006, the line was carrying around 4 million passengers a year and covering its running costs, though the construction investment remained unrecovered. Today, it remains a single 30-kilometer demonstration line rather than the beginning of a wider network. China went on to build its conventional high-speed rail at a scale that dwarfs everything else on Earth, while the Maglev stayed where it was, a remarkable technical statement on a short stretch of track. That may be about to change, because Japan is building something that would render even the Shanghai Maglev's top speed look modest. Japan has been developing its own maglev technology since the 1970s, pursuing a fundamentally different approach to Shanghai's German-derived system, where Shanghai uses electromagnetic suspension, which holds the train up by magnetic attraction from below. Japan's superconducting maglev uses electrodynamic suspension, cooling its onboard magnets to near absolute zero to achieve a state of superconductivity. The resulting magnetic fields are far stronger, lifting the train higher off the guideway and enabling much greater speeds. On April 21, 2015, a 7-car Japanese L0 series maglev on the Yamanashi test track hit 603 kilometers per hour with passengers on board, setting the world speed record for any manned vehicle on land, a record that still stands. The plan is to take that technology and build a line with it from Tokyo to Nagoya, and eventually onto Osaka. This is the Chuo Shinkansen, and it is one of the most ambitious rail projects anywhere on the planet. The Tokyo to Nagoya section alone runs 286 kilometers, and about 90% of that distance will be in tunnels bored through the Japanese Alps and underneath the densely developed urban corridor between the two cities. Commercial operating speed will be 500 kilometers per hour, which would carry passengers from Shinagawa Station in Tokyo to Nagoya in 40 minutes. Currently, the fastest train on that route takes about 86 minutes. When the full extension to Osaka opens, the trip from Tokyo to Japan's third largest city would take 67 minutes, a journey that currently takes around 2.5 hours. Construction began in 2014. The original target for the Tokyo-Nagoya opening was 2027. It has since slipped twice. In October 2025, JR Central announced the opening had been pushed back to no earlier than 2035 and revised the project cost upward to 11 trillion yen, roughly $74 billion, nearly double the original estimate. The escalation reflects soaring material and labor costs. plus the raw difficulty of boring through mountain terrain at the depth and precision this route demands. One tunnel section runs 1,400 meters below the surface of the Southern Alps. Ground movement near a work site in Tokyo's Shinagawa ward forced a temporary construction halt in 2025 while engineers investigated the cause. The Nagoya to Osaka extension is now targeted for around 2037, assuming the first section opens on schedule. By any measure, those costs and delays are significant, but so is what the line will actually do when it opens. 500 kilometers per hour as a scheduled commercial service would be roughly 70 kilometers per hour faster than anything operating today. Tokyo to Osaka in just over an hour for a corridor that already runs the world's busiest high-speed railway would be a transformation in how one of the world's most densely populated regions moves. The rest of the world is watching from a considerable distance. Europe operates high-speed rail across several countries, with France's TGV and Spain's AVE network consistently among the fastest conventional wheel-on-rail systems, reaching up to 320 kilometers per hour in service. The continent has around 8,500 kilometers of genuinely high-speed track compared to China's 50,000. The European Commission has proposed a €500 billion plan to expand cross-border connections, though most of its target milestones are decades away and dependent on aligning the infrastructure priorities of 27 different member states. The United States has a single corridor where anything approaching high-speed operation exists. Amtrak's Acela on the Northeast Corridor between Washington and Boston, which touches 240 kilometers per hour briefly in short segments, but averages well below that due to the age and curvature of the shared infrastructure it runs on. Two genuinely high-speed lines are currently under construction in the U.S., Brightline West connecting Las Vegas to Southern California, and the California High-Speed Rail Project between Los Angeles and San Francisco, though the California project has been under construction since 2008 and has not yet laid track on its central segment. No American line is expected to approach the operating speeds that China and Japan have built as standard. The gap is not closing, it is widening. These were some of the world's record-breaking megaprojects, but will their dominance last? Or will we soon see the rise of even bigger behemoths? Comment your thoughts below, and if you like the stories behind these impressive structures, check out our compilation on the wonders of the world where we cover the longest-standing ancient structure, a waterway that took thousands of lives, and 14 more incredible engineering achievements. Don't forget to subscribe to SIGNUM for more incredible documentaries about the world's biggest megaprojects.